I was just reading the latest clinical data on retinal photoentrainment, and it changes how we should evaluate circadian clock synchronization in healthy aging adult populations. Many people struggle with inconsistent sleep and daytime energy, assuming it is purely a result of late-night screen use as we navigate healthy aging during daily cognitive tasks. We commonly try to fix this by wearing blue blocking glasses at night, without considering our daytime light exposure patterns in our daily lives to protect our brain structure. However, neuroscience suggests that circadian synchronization depends on a specific, non-visual light input pathway in our eyes within neural tissues as we navigate healthy aging. Imagine a set of specialized light sensors that bypass your visual cortex to send a direct timing signal to your brain under these metabolic conditions in our daily lives. We are exploring how melanopsin expressing cells coordinate our internal clock, helping to reframe circadian health from screen avoidance to light optimization to support cognitive endurance within neural tissues. When this photoentrainment pathway receives insufficient daytime stimulation, the master clock in the brain drifts, disrupting sleep-wake cycles as we age over time under these metabolic conditions. If we focus only on avoiding light at night while remaining indoors all day, we ignore the synchronization signals required in healthy adult populations to support cognitive endurance. The stakes are high because chronic circadian desynchronization is associated with poor sleep architecture, mood changes, and accelerated cognitive aging for long-term health span as we age over time. Understanding the physical pathways of photoentrainment allows us to design practical, low-risk protocols that support our internal rhythms naturally during daily cognitive tasks in healthy adult populations. The problem is that modern indoor lighting is too dim to activate these specialized sensors effectively during morning hours to protect our brain structure for long-term health span. By identifying the specific biological mechanisms of melanopsin signaling, we can optimize our daily light exposure to support focus as we navigate healthy aging during daily cognitive tasks. To understand this timing process, we must define photoentrainment, the synchronization of our internal clock to the solar cycle in our daily lives to protect our brain structure. The master circadian pacemaker in mammals is the suprachiasmatic nucleus, a tiny structure located in the hypothalamus within neural tissues as we navigate healthy aging. This pacemaker relies on external light signals to adjust its period, ensuring cellular clocks throughout the body remain aligned under these metabolic conditions in our daily lives. This light signal is captured by intrinsically photosensitive retinal ganglion cells, or iPRGCs, located in the inner retina to support cognitive endurance within neural tissues. Unlike rods and cones, iPRGCs utilize the photopigment melanopsin, which is highly sensitive to blue light wavelengths as we age over time under these metabolic conditions. Melanopsin absorbs photons and initiates a slow, sustained depolarization that persists even after the light stimulus is turned off in healthy adult populations to support cognitive endurance. The axons of iPRGCs form the retino-hypothalamic tract, projecting directly to the suprachiasmatic nucleus without passing through visual centers for long-term health span as we age over time. During healthy aging, changes in lens clarity and pupil size can gradually reduce the light transmission to these vital sensors during daily cognitive tasks in healthy adult populations. As we age, the lens of the human eye naturally yellows, absorbing more short-wavelength blue light before it reaches the retina to protect our brain structure for long-term health span. This yellowing decreases the intensity of the light wavelength required to activate the melanopsin photopigment in iPRGCs as we navigate healthy aging during daily cognitive tasks. Consequently, the retino-hypothalamic tract transmits a weaker synchronization signal to the suprachiasmatic nucleus during morning hours in our daily lives to protect our brain structure. Without strong strong morning stimulation, the master clock's circadian amplitude declines, reducing the hormonal peak of cortisol at wakefulness within neural tissues as we navigate healthy aging. This flattened hormonal rhythm leads to morning grogginess and makes it difficult to maintain focus during early cognitive tasks under these metabolic conditions in our daily lives. At night, a weaker circadian signal reduces the natural surge of melatonin, delaying the transition from wakefulness to deep sleep to support cognitive endurance within neural tissues. This delay shortens slow-wave sleep cycles, the key periods required for the glymphatic clearance of metabolic waste products as we age over time under these metabolic conditions. This dual impact on morning alertness and night sleep shows that circadian health requires active daytime receptor stimulation in healthy adult populations to support cognitive endurance. Furthermore, iPRGC's project to brain regions that regulate mood and pupillary constriction, influencing cognitive energy independent of sleep for long-term health span as we age over time. If we spend our days under typical office lighting, which is significantly dimmer than natural daylight, iPRGCs remain understimulated during daily cognitive tasks in healthy adult populations. This lack of stimulation causes the internal master clock to drift gradually, leading to chronic, low-grade circadian desynchronization to protect our brain structure for long-term health span. This drift impairs synaptic plasticity in the hippocampus, illustrating that timing signals are essential for cognitive maintenance over time as we navigate healthy aging during daily cognitive tasks. The metabolic efficiency of our brain cells is closely dependent on the alignment of these circadian molecular clocks in tissues in our daily lives to protect our brain structure. We must examine the boundaries of this photoentrainment model to design practical, evidence-bounded daily protocols for healthy aging within neural tissues as we navigate healthy aging. By understanding the limits of current studies, we can establish realistic expectations for light-based circadian support strategies under these metabolic conditions in our daily lives. One limitation of photoentrainment research is that individual light sensitivity varies widely based on age and genetic factors to support cognitive endurance within neural tissues. We rely on indirect measures such as salivary melatonin assays, actigraphy sleep tracking, and pupillometry in clinical cohorts as we age over time under these metabolic conditions. In clinical studies, morning outdoor light exposure is associated with improved sleep quality, though individual baselines differ among subjects in healthy adult populations to support cognitive endurance. We must also recognize that circadian alignment is not regulated solely by light, as meal timing and exercise contribute for long-term health span as we age over time. The population boundaries of current trials are narrow, and we lack direct methods to measure suprasymptomatic nucleus activity in vivo during daily cognitive tasks in healthy adult populations. Because we cannot directly observe real-time melanopsin depolarization in living humans, we must interpret biomarker data with appropriate caution to protect our brain structure for long-term health span. Therefore, we analyze retinal photoentrainment as a key contributing pathway in circadian health, rather than a diagnostic marker as we navigate healthy aging during daily cognitive tasks. Answering our opening question, circadian synchronization is a daytime light input process rather than a simple nighttime screen issue in our daily lives to protect our brain structure. By understanding this physical mechanism, we can reframe our light habits, focusing on morning exposure to support our master clock within neural tissues as we navigate healthy aging. When photoentrainment is optimized, hormone cycles remain robust, which helps protect synaptic transmission efficiency and daytime cognitive focus under these metabolic conditions in our daily lives. The practical challenge is obtaining sufficient light intensity within modern indoor work environments and daily schedules to support cognitive endurance within neural tissues. While we cannot prevent the natural aging of the lens, We can optimize the availability of environmental light signals as we age over time under these metabolic conditions. Seeking natural outdoor light for at least 10 minutes shortly after waking stimulates iPRGCs with the required wavelength and intensity in healthy adult populations to support cognitive endurance. Avoiding bright light exposure during late evening hours helps prevent the unwanted phase shift that delays melatonin release for long-term health span as we age over time. These simple daily habits do not target memory storage directly, but they support the temporal alignment of all brain systems during daily cognitive tasks in healthy adult populations. Supporting circadian synchronization requires a unified focus on morning light, evening darkness, and consistent sleep timing to optimize these pathways to protect our brain structure for long-term health span. To apply these insights, seek natural sunlight for 10 to 15 minutes shortly after waking to support morning synchronization as we navigate healthy aging during daily cognitive tasks. If natural sunlight is unavailable in the morning, consider using a bright light box designed for circadian support in our daily lives to protect our brain structure. Limit exposure to bright screens and overhead lights in the late evening to facilitate the natural rise of melatonin within neural tissues as we navigate healthy aging. Consult a healthcare professional if you experience chronic sleep-wake disturbances, as persistent circadian misalignment can impact overall health under these metabolic conditions. Avoid relying on high-dose melatonin supplements to manage your sleep schedule without professional guidance, as they can alter hormone sensitivity to support cognitive endurance. Please remember that this analysis is intended for educational purposes and should not replace individualized clinical evaluation or specific medical advice as we age over time. Focus on establishing consistent, low-risk daily habits that support natural light exposure and reduce systemic metabolic stress naturally in healthy adult populations. Track your morning light exposure, sleep consistency, and daytime focus to build a personalized, evidence-bounded framework that supports your health span for long-term health span. Optimize the protocol, protect your brain, and I'll see you in the next data set.